Greetings to you. We were discussing about radiation sources for atomic absorption spectrometry. What we had discussed was about hollow cathode lamp as one of the sources of radiation, which will give out the radiation of the same element which you want to determine, and because the filament is made of the metal which you want to analyze. The filament is in the form of a conical cylinder, and we had discussed at length about these things. I do not want to repeat this, but we will move on to another source of the radiation, that is known as vapor discharge lamp. Here you can see that the construction is almost similar to the hollow cathode lamp. It is a long tube and then made of pyrex at this end, or quartz window at this end, okay. And then there is a vacuum inside, and inside this hollow cathode tube we have the connectors here, and then the sample is wound around this ceramic tube. It is a refractory ceramic tube, okay. And if I want to make a copper estimation, I wind a copper wire along this vapor discharge lamp. So, it is all insulated nicely, and then we have the lamp is ready for use. So, essentially the remaining part of the hollow cathode lamp remains the same, and there is a glow discharge which from neon or argon, whichever gas we use, and later on the initially glow discharge will start, followed by the wire, okay. So, very volatile materials like mercury, thallium, zinc and alkali metals can be determined using low pressure vapor discharge lamps. Why only these things? Because we do not really create the discharge as like flame, and we simply use the material as such. They can be of low cost and give high radiant intensity, because these elements are easily converted into vapor phase. They emit strongly broadened lines owing to self absorption and self reversal, because if the vapor concentration is more, there will be lot of self absorption. This we have already seen in the case of sodium lamps in our street light example. So, EDLs must be operated at highly reduced currents. So, the current requirement is very less, but if the current requirement is very less, it leads to instability of the lamp also, okay. So, these are some of the problems with the materials, and they are not so common as EDLs, hollow cathode lamps, because hollow cathode lamps are made of the same filament, etc., and they are made very easily, and then it is difficult to make. Very few lamps are usually made of this EDLs, electrodeless discharge lamps, because only volatile materials need to be converted into vapor phase. Now, the volatile materials means at very low temperature the material should vaporize. That is the idea. So, we just coat the copper wire or some other wire with volatile materials like mercury, This I already told you now. This mercury, thallium, zinc and alkali metals etc. And when we heat them, the discharge takes place. Now I am going to discuss another type of lamp, that is known as electrodeless discharge lamp. So, as the name suggests, we have there are no electrodes in this. What we have? We have a quartz window here in this side. You can see the plain portion of this region, that is a quartz window, and this is an RF coil, radio frequency coil, wound around a ceramic holder. Okay. And then here you see there is a small cavity. In this cavity we put our materials which we want to get discharge. You can put any salt, for example. So, this is the salt containing bulb and this is the RF coil, this is the front view. So, one side is quartz window, the other side is connector. So, essentially it is a very simple operation, only thing is there are no electrodes here, only the salt is deposited inside the cavity of the ceramic tube on which an RF coil is wound. So, how does it work? Yes, this is known as electrodeless discharge lamp because there are no electrodes, and these things exhibit highest radiant intensity and narrowest line widths compared to hollow cathode lamps, because basically the salts ionize and then they will pick up the electrons from the neon or argon glow discharges. So, it consists of a sealed quartz tube of about 5 to 10 mm dia, 4 to 5 centimeter length, and it is filled with a few milligrams of the analyte element. This is a very important aspect of any atomic absorption. You need to have a salt of the what you want to analyze. You can put the element itself or its salt also. This tube is filled with argon, that is to set up the glow discharge. So, the lamp contains no electrode, but it is energized by an intense field of radio frequency. The tube is mounted within the coil of a high frequency generator. The range is about 2400 megahertz and it is excited by an output of about 200 watts. So, these are the technical details of 2400 and 200 watts etc. They can vary for different elements. This point you should remember, and also you should remember that the design of this can vary from instrument to instrument. In fact, most of the instrument manufacturers change the design, this length, width and then diameter and then connectors like that to suit their models, so that they are also not applicable to other instruments. So, it becomes sort of intellectual property also, the design. Okay. So, we have this they may change this generator frequency, they may change to from 200 to 150 watts or 250 watts. So, what happens is, if the minimum if you want to fit the lamp of one instrument to another instrument, for example, Perkin-Elmer to GBC or some other manufacturer, they would set the limit at 2200 hertz. Then what happens? If your instrument is not designed to take 2400, if it will not take 2400, but the EDL of another company, another manufacturer would require 2400. So, it will not work. Same thing is true with respect to wattage also. They will say we will set it up at 150 watts, that they will not tell you in the technical literature. It is only manufacturer's data, and they will say you buy our EDL and then electrodeless discharge lamp and use it. And if you want to use somebody else's, then it has to take 200 watts. Suppose the instrument itself is supplying only 150 watts, definitely other EDLs will not work. Plus there are other safeguards they normally employ, such as position of the connector and other things. So in general, what we see across the market is most of the hollow cathode lamps or electrodeless discharge lamps or vapor discharge lamps, all these things normally are suitable for a particular model and for a particular company belonging to that company, because models may change, but still the material, the electrical connectors and other things will remain the same. So it becomes intellectual property. So we are forced to buy EDLs and vapor discharge lamps from the same company if you are using a particular model. So this point you should remember. Of course, there are nowadays there are interconnectors which will help you to some extent, but not all the time. Okay. So these are the three main radiation sources for atomic absorption spectrometry. There are others also. For example, you can use a xenon lamp. A xenon lamp gives you very high intensity radiation at all wavelength frequencies, right from UV to visible. But a xenon lamp has short life, etc. There are other problems which have been solved to some extent in recent instruments. But before we go to that level, we will take a look at the chemical aspects of EDL. So the EDLs are ideal for elements whose resonance lines are below 200 nanometers. This is an important aspect, because earlier I had said that several elements like iodine, arsenic, etc., they have resonance lines less than 200 nanometers. Now here we have, if I use a vapor EDL, electrodeless discharge lamp, I have a chance of using such elements, such EDLs, light sources, because EDLs give you very high intensity radiation and very narrow bandwidth. So what are such elements? These elements are arsenic, selenium, phosphorus, iodine, etc. Iodine is not there usually, nobody determines iodine by atomic absorption, but EDLs are nowadays available for most of the volatile elements, including cesium and rubidium. Actually the work function of cesium is very less, but so it is used in detectors, but even for atomic absorption cesium and rubidium EDLs are available. So if you use an EDL, what are the detection limits? So how do you compare the detection limit of EDL with anything else? The only reason is to compare the sensitivity, that is the lowest quantity of determination of the element, with other radiation sources. So the what are the other radiation sources? The EDLs are not available for elements like arsenic, etc. You have to compare only with hollow cathode lamps. Electro discharge lamps are not available for all elements. So the EDLs, even though they are not so common for every element, but the detection limits what you are going to see are about 2 to 3 times lower than HCl. For example, if with HCl you are able to determine about 10 micrograms per liter or 10 ppb, with EDL you can go to 3 micrograms per liter, still lower quantities can be determined. And we will discuss about the trace element theory of trace element determination at a later stage when we complete the atomic absorption studies, and then when we move towards applications. So, they are also very stable. EDLs are very stable during operation and have long lifetimes. So, HCl, I have told you that they have a very short lifetime, maybe about 2 liter, 2 to 3 years, but EDLs have longer shelf life. So, what are the conclusions? The conclusions are EDLs and HCl, hollow cathode lamp, are complementary to each other. What cannot be determined easily with hollow cathode lamp, we should determine by electrodeless discharge lamps, okay, or vapor discharge lamps also are possible. Now, there are, as I was telling you, we look at continuum sources. So, continuum spectrum of hydrogen, xenon, halogen lamps, etc. offer good stability. They are cost effective and exhibit multi-element capability. They are that means you can, because it is continuous, several elements are detectable, because continuous spectrum means almost all lines are available in the spectrum. So, you can choose by putting a monochromator, you can choose any wavelength from the continuum corresponding to an element whose resonance line falls in that region. Okay. So, what we are saying is the whichever element gives you a continuum spectrum in the UV and visible range, you should be able to determine theoretically atomic absorption method. You should be able to use atomic absorption for the determination of elements, but the only condition is the continuum portion of the spectrum must be also be very highly intense. This does not happen. For example, even for hydrogen, etc., very few lines are really strong lines. That means they when you collect them on the photographic plate, you should see a very dark line corresponding to that resonance line. So, the hydrogen, xenon and halogen lamps normally offer good stability. They give you continuum spectrum also, but among these only xenon lamp has picked up somewhat, and nowadays I am seeing in the market xenon lamps are being offered for atomic absorption spectrometry. Now, what are the advantages of a xenon lamp? One thing is it gives continuum, so you can determine any element from the UV and visible range, and one single source is enough, that is xenon lamp, correct. So, if I use a xenon lamp, I do not need a hollow cathode lamp, I do not need electrodeless discharge lamps, I do not need vapor discharge lamps, only one source will do. So, such instruments have become available since last 2-3 years only maybe earlier they were curiosities, scientific curiosities, but nowadays commercial instruments have become available where you can use a xenon lamp, which will obviate the necessity of purchasing a hollow cathode lamp for every element. So, this is one advantage. The other but there are disadvantages with halogen lamps also. What are they? The lamp becomes very hot. So, you need to circulate cold water around the xenon lamp to keep the lamp in good working condition, otherwise their lamp may not work for long time. So, continuous cooling of the xenon lamp is necessary, and also the optics will change, because the same optics has to choose from a continuum spectrum particular line. In hollow cathode lamp, it is only one line one or two resonance lines maximum I can use. So, I can use a monochromator made of only glass filter or a simple quartz filter or a quartz prism. I can use it, but if you want to use a xenon lamp, you need to have a proper monochromator which can give you very good accuracy of the wavelength what you want to choose. So, these are the other things. So, if you take a look at this slide, you will see that the low intensity of the chosen wavelength, that is corresponding to hydrogen and halogen, not xenon, the intensity would be low. So, high demands on the monochromator. Monochromator performance should be extremely well. So, what it should produce? It should produce an accuracy of 0.002 nanometer wavelength, and there will be risk of spectral interferences always, and they had not become popular, but nowadays the technical problems of xenon lamps have been overcome and such instruments are available in the market. Okay. So, now we move on to atomizers. So, what is an atomizer? The requirement of the production of free atoms in the optical path of the radiation coming from the hollow cathode lamp, I need to put a mass of free atoms of the element which I want to analyze. Okay. So, the atomizer is a space in between the hollow cathode lamp and the monochromator and the detector on the other side, and that atomizer should have a mechanism to produce free atoms from the sample which you want to analyze. Earlier I had told you that the most of the samples which we want to analyze in atomic absorption are in the aqueous state, are in the liquid state. Most of the samples are dissolved in acids and diluted to get solutions, and this solution needs to be converted into fine vapor containing ions, and those ions will pick up electrons from the flame and they become atoms, free atoms, which is ready to absorb the radiation coming from hollow cathode lamp. So, the job of the atomizer is to produce free atoms, and the liquid must be converted into ions first, vapor and then ions and then into atoms. So, this is easily accomplished by spraying the analyte. You can look at this slide now. What I have written here, the atomizers transform a liquid sample into atoms. This is easily accomplished by spraying the analyte solution into a flame, where the ions or molecules are converted into atoms. So, is this the only mechanism that is available to convert a sample into a vapor? No, the answer is no. There are other techniques of atomization that include, I can heat it, electrothermal evaporation, I can produce a hydride generation, which I had mentioned earlier a little bit earlier I had mentioned you, and there is a cold vapor technique, that is also we are going to discuss it later, and the success or failure of atomic absorption determination is virtually dependent upon the efficiency of atomization. So, the total number of atoms that are formed determines the sensitivity. Now, you should imagine that there is a flame here space in which atoms are being produced here, and then I have a small pipe from the bottom which will spray the liquid. You would have seen number of sprayers, garden sprayers, this sprayer and can sprayer and window cleaner, most of them are sprayers. So, what I do normally is I take a sprayer, put the sample through the sprayer and press it. So, what happens, a fine mist of the liquid will form, and that liquid I am taking it into the flame space. Okay. I will show you a diagram corresponding to that, but before that what you should realize is the job, since the job of the atomizer is to produce free atoms, the more free atoms I produce, more would be the absorbance, more would be the number of atoms in the ground state, which we have already seen earlier that at any temperature the atoms in the ground state are at lower ground state. So, if my efficiency is more, there are more atoms in the ground state. So, more atoms will absorb the radiation. So, if I am measuring the radiation, if there are more atoms, radiation coming out would be so much less. If there are less atoms, radiation will be more. If there are more radiation, radiation coming out will be less. If there are no element, if there are no free atoms, then the radiation will remain unchanged, that is 0 concentration. At 0 concentration, the radiation what we collect from the atomizer would not be affected because there are no free atoms. Suppose I pass only water, then what happens? I want to determine copper, there is no copper in water. So, when there is no copper in water, there are no free copper atoms. So, the radiation incoming and transmitted radiation will be same. So, if there are about 100 atoms in the copper solution, radiation will be so much less corresponding to 100 atoms. If there are 1000 copper atoms in the ground state, I will have more absorbance and the transmitted radiation will be so much less. That is the logic of using an atomizer. So, look at the slide now. The success or failure of atomic absorption spectrometer is virtually dependent, absolutely dependent upon the efficiency of atomization, that is the total number of atoms that are formed. Okay. So, this point I hope I have driven well, and the most easiest way of determining producing a free atom population in the optical path is a pneumatic nebulizer. So, what is a pneumatic nebulizer? The nebulizer is one which converts a liquid into a spray. A pneumatic nebulizer is it converts because of air pressure. Okay. Because of the air pressure, it will push out the liquid and produce a spray. You can imagine any plastic, simple plastic bottle in which liquid is put and you press it, liquid will come out, and if you put at the exit point, if you put number of holes, small holes, vapor will come out into small jets, and if the hole is small enough, then it will produce small droplets in the space that is immediately outside. So, and that is a pneumatic nebulizer. Pneumatic nebulizer is very useful to spray the sample into a flame in a continuous manner, because we do not want to do it manually every time. We want to do it in a continuous manner. So, to maintain a steady supply of atoms, because in the flame, if you remember, a flame is a dynamic system. Flame is burning, I want to introduce my sample. So, what happens to my sample? My sample also keeps on flying out of the flame after some time, maybe a few microseconds. it is there in residing in the flame, and then it will move out because more atoms are coming from the bottom. So, after some time what happens is the number of atoms coming into the flame and number of atoms going out of the flame will match if I have a steady supply of the liquid. Okay. So, because of the steady supply, that is what we want. The number of atoms entering the flame, number of atoms leaving the flame are essentially same. So, this kind of steady state is required in atomic absorption spectrometry. So, usually look at this slide now. Nebulizers, what the job is to spray in a continuous manner. Look at the slide. I want you to understand this. Continuous manner to maintain a steady supply of atoms is a must. Usually they are connected to the flame burner through a small capillary, which can be considered as a single unit, even though both parts are detachable and serviced independently and reconnected. So, typical design of a laminar flow burner is shown here. This is the atomizer or nebulizer and a burner assembly in atomic absorption spectrometer. We will continue our discussion in the next class.